Well, I don't know about the rest of you, but I'm logged into Second Life on my Commodore 64 right now. It's working pretty well. I've got about 120 frames per second frame rate at full graphics resolution. Commodore 64 does pretty well. The Commodore 64 didn't actually have 128K. That was the Commodore 128. The Commodore 64 had 64K. Actually, what it was is it only had 64K of address space. And so some of that was used up for the ROM. You ended up with effectively about 40K of free RAM. Commodore 128 also could only address 16-bit, but it had this memory management unit that had ways of fetching stuff from other banks, and it supported up to something like 8 banks, but it only used 2. Yeah, I used a Commodore 64 a lot back when I was in high school, and a Commodore 128 when I was in college. Yes, voice is on. Yeah, 128 was my favorite. Using my Commodore 128 probably 5 or 6 years after it was effectively obsolete. It was sad when I sold my last one. I don't have any anymore. I don't have any Amigas anymore. The world has just moved on. Oh, I know, 40 meg. I mean, I think about even in the 90s when I would install Linux on a machine, I could get a 200 meg hard drive, install everything from Slackware, and half the drive was still open. Nowadays, if you try and update to the new version of Debian or something, and if your root disk doesn't have 10 gig free, it won't even do it. It's terrible. So everything's huge. I guess I'll go ahead and get started. So hello, everybody. Welcome to the Science Circle. I am Rob Knop. Sometimes I am known as Prospero Frobaz. It's very confusing. I have a lot of identity problems, and that's just the beginning of them. But today I am going to be talking about colliding neutron stars. My title was a little ungainly, and I know the title I sent to Jess was ungainly, and the title here is not quite the same, and it's ungainly. And I guess I didn't ever find a good way to have a title that expressed everything I wanted to express without just going ahead and saying, never mind, and I'll come up with a good title like Dragons Clashing or something like that. So Dragons Clashing might be a good thing. It's a reference to the Robert L. Forward novel, Dragon's Egg, but whatever. Instead, what it is actually, it's really cool. Skip everything to gold. Okay, there was gold. Any questions? Okay, we're done. Bye. No, so what it is something that's really cool because, first of all, 2 neutron stars ran into each other. Now, we think we've seen lots of those before, but this is the first time we've really had a strong confirmation of it. And whenever big, dense things run into each other, it's always pretty exciting. I don't know why. Maybe just because I'm an American, so I like explosions. But another thing that's really cool about this is that this is one of a very rare sets of multi-mode astronomy. Or multi-messenger astronomy, I think is what one of the papers about this called it. We have had that before. I guess the first real incidences of multi-messenger astronomy sorta happened once astronomers realized they could use infrared light or radio light, but that was still all electromagnetic. In the solar system, of course, we've even gone and sent robots to dig things up and do experiments on it. But outside the solar system, to my knowledge, if I am not mistaken, there's only one other object that we got more than one kind of data on, and that was supernova 1987A, where we got both light and neutrinos from. Yeah, cosmic rays. I guess that's a good point, right? Although even there, cosmic rays, we just get the particles come flying in. And I don't believe we have connected specific cosmic rays with any specific event that we've seen in the sky. We believe that a lot of cosmic rays come from supernova, but it's more of a statistical thing. There have been lots of supernova, and now there's lots of cosmic rays. So 1987A was observed in both light and neutrinos. We have observed things before in gravitational waves. Of course, the Nobel Prize this year went to the discovery or the direct detection of gravitational waves. Colliding black holes, big old black holes, although I just read a few days ago they had a couple of modest mass, sort of 2 to 3 to 10 solar mass black holes colliding, which is good because, everybody wants to collide. But this time we had not just all across the optical spectrum. So there was gamma rays and ultraviolet and optical and infrared and radio, all of that. We also had gravitational waves, all from one object. So that's pretty exciting by itself. This is the first time we've detected something in gravitational waves and been able to connect it to other observations. And considering gravitational wave detections are only a couple years old, that's pretty good. Not even a couple years old. But it also has confirmed things about some of the objects we're looking at. So to dive in, I need to start by talking about gamma ray bursts, because the event that was observed was a gamma ray burst. Although you say, wait, Rob, you just told it was two neutron stars colliding. Well, okay. So we have this thing in astronomy that we usually name things after what they looked like before we knew what they were. So supernova, we called because it was more luminous than a nova, and nova we called because it's new, and it was a new star, and it was a star that did not appear to move like a comet or a planet, but that hadn't been there before. And then later we discovered that there are two very different phenomena that put out similar amounts of energy that are called supernova. Well, similarly, there are gamma ray bursts, which were first discovered back in the late 60s, early 70s. I think when they were first discovered, it was discovered by military satellites looking for nuclear tests, and so they were classified at first. But before long, they realized, wait a minute, these are coming from kind of the opposite direction that nuclear tests would. They're coming from space. And so for a long time, gamma ray bursts were sort of a mystery. They were seen at the rate of roughly once a day, and they would be very luminous in gamma ray, or very bright, I should say, in gamma rays, and then they were short, and they would go away. And nobody knew what they were. And then in the 1990s, so when I was early in grad school, now that I'm getting old, now that I'm almost 50, I like to talk about how kids these days, you just don't understand what it was like back when I was your age. I am boggled to think about how different the world is compared to what it was when I was a freshman, when I teach college freshmen. Things like, we only knew about planets in our own solar system. We didn't know about them anywhere else. When I was in so one thing is, when I started grad school, gamma ray bursts were a big mystery. And one of the cool things about that is that when something's a big mystery, is people come up with all kinds of crazy, wacky ideas to explain it. I would say that Tabby's star, or Boyega's star, is an example of that right now. Nobody knows exactly what it is, so we can, there's still at least the very faint possibility that it's highly advanced aliens. That's not what I bet on, but, we haven't completely ruled it out. So gamma ray bursts, we didn't know where they were coming from. We didn't know if they were in our galaxy or if they were coming from the whole universe. I think there was even models like antimatter and matter comets colliding in the Oort cloud, which is kind of fun to think about. And of course, the models went all the way up to interstellar war. My own personal model was that, you remember before we turned on the relativistic heavy ion collider, which and the same thing happened when we turned on the LHC. People was afraid it was going to destroy the Earth. With the LHC, it was create small black holes that would eat up the Earth. With RIC, which is in New York somewhere, on Long Island, I think, the problem was it was going to nucleate strange matter and destroy the Earth and destroy the whole solar system. So my model was the gamma ray bursts were alien civilizations turning on their heavy ion colliders and destroying their entire civilization. But then we tested my model by turning on our heavy ion collider, and we didn't die, so my model was disproved. But somewhere in the early 1990s, we figured out from this instrument called BATSI, actually. So that's the plot I have behind me, the upper left plot. BATSI here on this upper left plot, these plots are, each spot is where on the sky a gamma ray burst was seen. This is a galactic coordinate plot, so the plane of the galaxy would go across the center of this plot, and then this is the whole sky. You've seen projections of the Earth like this. So this is a projection of the whole sky, and what you should more or less see is that the colored dots are pretty uniform over the whole sky. And once BATSI released that, it became very clear that these were at cosmological distances. They did not correlate with our galaxy. They certainly didn't correlate with our solar system. They had to be at cosmological distances. Which was cool, partly because it meant, okay, they're really luminous. But another thing we sort of learned as we learned more about gamma ray bursts is that we could divide them into two categories. And of course, that's how we always do things. We find something and eventually we divide it into two categories. Because we start to notice the first bit of detail we can about it. And it turns out these two categories were very meaningful. So on the lower right plot, you can see that they're divided into long duration and short duration bursts, although even the long duration bursts are short compared to astronomy. So the long duration bursts go up to something like 1,000 seconds. That's a little more than 15 minutes, which is nothing for astronomy. You know, I think of a star that's 50 solar masses lives 1 million years, and that basically means it dies immediately after it's born. And then somewhere around maybe 2 seconds, you can see that there's an overlap, but there's a second peak down here at less than a second. Those were called the short duration bursts. And by the end of the 1990s, or maybe it was in the early 2000s, eventually, I actually think it was actually the early 2000s, we had figured out that the long duration bursts were associated with supernova. We eventually were able to get some optical, so standard visible light telescope follow-ups of gamma ray bursts. When we looked and found the optical fading thing in gamma ray bursts, we were able to associate gamma ray bursts with particularly powerful supernova, sometimes called hypernova. What's really going on with these things is that when they, well, I have another slide. In fact, I'll just go to the next slide and tell you about them. Well, okay. Actually, before I tell you about that, I want to tell you about all stars. So I apologize for having gotten ahead of myself. But to make sense out of this, I'm going to tell you about what stars do in general. So stars spend their life in hydrostatic equilibrium, which is a fancy word for there's a balance between the star trying to collapse under its own gravity and then pressure holding it up against that. This is a slide. I actually used this in my astronomy class just last week, maybe the week before. And I didn't tell them that the slide was just a screenshot of a thing I made in Second Life quite a while back. So I have the original 3D object here if you look behind me. In fact, here I'll move it out a little bit so it's easier to see. So warning, gigantic star about to show up in the middle of the world. Okay, there it is. This was supposed to be a star, and hey, it's a cutaway star. So notice that when I cut it away, and let me rotate it so the cutaway is more visible, it looks like you can sort of look in and see the core of the star. Which, of course, in Second Life, I make the core of the star just a glowing sphere. But whatever. It's roughly right for our sun, approximately the size of the core. And right at the core of the star, nuclear fusion is ongoing. Why at the core of the star? Because it's really hot and really dense there. And it's really hot and really dense there because of all the gravity. So these blue arrows are meant to represent the gravity pushing in. Gravity is pulling all the mass, a full sun's mass worth of stuff, which really crushes down on the center of the star. But then to fight that, at the center of the star, nuclear fusion creates energy. A lot of that energy goes into photons, gamma rays that come out. Some of it goes into just heating up the plasma around it, getting it moving really fast. And the result is that there's a lot of pressure coming out from the center of the star. And so there's this constant balance between gravity and pressure that keeps the star at a very constant size, a very constant luminosity. If it got denser, it would increase the rate of nuclear fusion. So the nuclear fusion tends to push it out a little and then it slows it down. It's a nice balance. And we're pretty happy about that because it allows us to live on the sun. Sorry, we don't live on the sun. That would be too hot. It allows us to live around the sun on our little planet with a nice, very stable sun that's been stable for a long time that allows us to have life and all that kind of fun stuff. I'll move this guy back out of the way. So that's what's going on in stars most of the time. And in fact, I'm going to close it up so it's not too distracting. Good. That's what's going on in stars. But at the end of a star's life, at least a very massive star. So at the end of the sun's life, the sun's not dense enough to actually do all that much fusion. It'll fuse hydrogen to helium for 10 billion years. It'll fuse helium to carbon for about 1 billion years, and that's all it'll ever do. But really massive stars can compress their cores. And so this is a star not long before the end, right? It's sort of like the Roman Empire just before it falls, except this is a star. So it's not like the Roman Empire at all. Here's your star. It's a big distended supergiant star at this point. And At the core of the star, there's an inert iron core. It turns out if you want to do fusion of iron, you have to put energy in. You can't generate energy by doing fusion of iron. So the iron just sits there, and it's extremely dense. And then around the iron, there's a shell. So imagine this as a spherical shell of silicon doing fusion up to iron, and outside that oxygen, and outside that carbon, and outside that helium. And then finally outside there's hydrogen fusing to helium, and outside that is the envelope of the star with no fusion. So you've got this kind of nuclear fusion onion structure going on. But when the iron core reaches a limiting mass, a mass of 1.4 times the mass of the sun, the quantum forces that are holding it up, it really is this thing called Fermi degeneracy pressure, which is effectively all the electrons are packed into quantum states as tightly as they can. Eventually, relativity and quantum mechanics kind of fight a bit, and quantum mechanics just can't hold it up anymore, and the whole thing collapses. Boom, you get a core collapse supernova, as we call it. Boom, pretty exciting. And in the core collapse supernova, sometimes, if it's a really big star like that 25 solar mass star I told you about, the core collapses, what I like to say, all the way, which means it becomes a black hole. The core collapses so that something like 2 to 10 solar masses of material get stuck behind an event horizon. And what exactly happens to it there? There's two answers. One is, I don't know, and the other is, it doesn't matter, because once you have an event horizon, nothing inside can get out, but you've got huge gravity. But not all of the star goes into the black hole. Some of it gets ejected out in the explosion. And if you happen to be looking in the right direction, so you have, this is supposed to be here, this blue circular thing is just the regular old supernova that we would see as probably a type 1c supernova, a core collapse supernova. But if you happen to be in this direction, looking over here, you will see a gamma ray burst, because along the angular momentum axes of the explosion, it squirts out these two jets and then shocks. Basically, the material doesn't all squirt out at exactly the same speed, so some of it crashes into the stuff in front of it. You get shocks, you get back shocks, all kinds of stuff happens. Some people spend their life trying to model the fluid dynamics of all of this. And you get these shocks, and it can put out huge amounts of energy. Yeah, don't stand in the way of a gamma ray. Oh, actually, you know what? We stand in the way of them a lot. That's how we observe them. So if you're not in the way of them, you won't see them. But don't be too close when you stand in the way of a gamma ray burst. Right? It's a little like a fireworks on July 4th, right? They're fun to watch, but if they happen right under you, it's bad. Gamma ray burst, if it happens anywhere in our galaxy, you kind of don't want to have it pointed at you. And some people have even hypothesized that one of the mass extinctions in our history was caused by a gamma ray burst in our galaxy, illuminating our planet with lethal gamma rays. So, you know, personally, I lose more sleep over the word super volcano, but you can lose sleep over whatever you want. So gamma ray bursts, these are the long duration gamma ray bursts. And again, remember, long duration is 10 to 1,000 seconds. So really not terribly long on the astronomical scale, but, you know, more than a second is what we call long for a gamma ray burst. The long duration gamma ray bursts, and they are pretty well associated with supernova now. We've seen a lot of cases where we can observe the optical supernova and the gamma ray burst at the same time. So that's a long duration gamma ray burst, one of these really massive stars dying. Now, it turns out, if the star wasn't quite 25 solar masses, but was between 8 and 15 solar masses, it actually does not leave behind a black hole. It's only the most massive stars that leave behind a black hole. Smaller than 8 solar masses don't even supernova at all. They are what we call low mass stars. Although that when you use the word low mass, you have to make sure you know the context you're talking about. I have known people whose research would consider the sun an extremely high mass star. But from my point of view, because I care about supernova, the sun is a low mass star because it doesn't go supernova. So the high mass but not super high mass stars will, you know, those between 8 and 15 times the mass of the sun, when they explode, the core collapses down to a neutron star. So it doesn't collapse all the way to a black hole, but eventually, whereas before you had the electrons packed together as close as they could be, the oversimplified way of looking at it is the electrons and the protons get squished together to make neutrons, and now you have neutrons packed together absolutely as close as they can be. Although this image here suggests there's actually sort of an interesting structure to it, that even there's, you know, you might call there's the outer crust, which maybe even sort of has a weird atmosphere-like thing about it, and then inside, of that, you're going to have nuclei, and inside of that, you're going to have a neutron, proton, Fermi liquid, and a few percent electron Fermi gas, and that's where it's more like a classic neutron star. Then actually at the very core, it might not be neutrons at all. It might actually be quarks and gluons freely tooling around and doing their fun thing. That's great. But the point is that you have a star that's maybe 1.5 to 2 times the mass of the sun, but it's only 10 kilometers in radius. So I mean, you could walk 10 kilometers. Not me. I'm kind of too lazy, but you probably could. So that's a lot of mass in a very small area. You may have heard of a white dwarf star, which is the mass of the sun, but roughly the size of the Earth. That's already freaking dense. This is an entire 10-kilometer radius thing that's the mass of an atomic nucleus. Not the mass, the density of an atomic nucleus. So this is a really, really, really dense thing. Where do they come from? High mass stars, stars between 8 and 15 times the mass of the sun. When they end their life, because they've done fusion all the way up to iron at their core, and basically they run out of fuel. They have no more fusion they can do to support themselves against gravity. Gravity wins. The core collapses. There's a big explosion. All kinds of fun stuff happens. And then the neutron star is left behind. So that's where all the neutron stars come from. It's a little like squishing old cars in a compactor, except the compactor is kind of from the inside in this case, because, you know, it's the gravity pulling down. So that'd be a good thing to design, right? This little thing you stick inside a car, and then it pulls the whole car into on it, and you just have a little ball-shaped thing that you can kind of pick up and toss around and maybe have a sport, because, you know, that's what it's all about. Neutron stars, we have observed neutron stars for decades. They were originally observed as pulsars. So what happens with a pulsar is the neutron star has a tremendously strong magnetic field. It takes, basically you take the magnetic field of the sun, but if you take a magnetic field and you squish it to a smaller volume, the field gets way stronger. So you take the volume of the sun, or actually, yeah, roughly, so volume of the sun, or maybe bigger than the sun, and you squish it down to the size just to 10 kilometers, you get an amazingly strong magnetic field. What's more, because a supernova just happened, there's all kinds of charged particles around the pulsar. So the magnetic field, and so these loopy lines here are supposed to represent the magnetic field. They look sort of like if you've ever seen a picture of the magnetic field of the Earth, only way stronger. Charged particles can get caught in these loopy lines. Now the same thing happens around Earth. Charged particles get caught and they just spiral around the loopy lines. And what happens is they'll spiral up here. I'm looking spastic as I click a lot. And eventually, where all the lines come together, it gets down close to the Earth. The charged particles crash into the Earth's atmosphere and put energy into the atmosphere and cause it to radiate, and we see that as an aurora. On a neutron star, first of all, the magnetic field is way stronger. Second of all, the gravity of the star is way huger than the gravity of the Earth once it crashes into the surface. So it's a tremendous amount of energy, and right where it crashes, you get a hot spot. And so then as the neutron star rotates, if the axis of rotation, which is this green line here, is not lined up with the hot spots, then as it rotates every so often, one of the hot spots is going to be pointed at you. And many of you have seen this before, but I have a little simple pulsar 3D guy. Let's see, is this it? Yep, there it is. Neutron star, and it's rotating vertically, but there's two hot spots. I don't have the magnetic field here. And as you look at it, every so often you see a bright spot pointing at you. And especially when the bright spot points right at you, you would see that as a brief pulse of light. So pulsars are observed in radio waves. They're also observed in gamma rays. And there are optical pulsars as well. I think classically, radio waves is how we would observe most of them. But the Crab Nebula, for instance, has a pulsar that's been observed at all wavelengths. So pulsars have been known since the 60s. When they were first discovered, we didn't know what they were, but we quickly figured out that, yes, they are these neutron stars with huge magnetic fields and hot spots, rotating neutron stars. So neutron stars we've known about for a long time. Now, one of the cool things about pulsars is, again, a couple decades ago, some people discovered a binary pulsar, so two pulsars orbiting each other. Because the rotation of pulsars is very regular, you can get extremely precise timing out of them. From this binary pulsar, they were able to time the rate at which the orbit was decaying. So as the pulsars orbit each other, sometimes they're coming towards you, sometimes they're moving away, and that will change the timing of the pulses. If it's coming towards you, the second pulse, two pulses in a row. The second one sort of has a head start because the stars come a little closer. And so the time between the pulses will be less than they would have been otherwise. And the opposite when it's going away. Well, so using this timing, they could measure the decay of the orbit. The two neutron stars are spiraling in slowly on each other. And the decay exactly matched the prediction of what the decay should be from gravitational waves. So many people viewed that as confirmation of gravitational waves as a phenomenon. And that was back in the 70s, and since then we have even better data on it. So neutron stars have been connected with gravitational waves for a while, but it was an indirect observation of gravitational waves. It was just the orbit of neutron stars was decaying at the rate you would expect from gravitational waves. Right, so we know about neutron stars. We know that there are such things as binary neutron stars that orbit each other. And that led us to the most likely, and for a long time, basically for the last, I don't know, decade or something, it's been the accepted explanation for short duration gamma ray bursts. So remember, the long duration gamma ray bursts, typically durations of 10 to 1,000 seconds, are from really massive stars exploding. The short duration gamma ray bursts were thought to be when two neutron stars collided with each other. And since we've seen a binary pulsar where the orbit is decaying, it's going to happen. If you have two neutron stars orbiting each other, if they're close enough, gravitational waves will suck energy out of the orbit, and eventually they will come together and crash with each other. And so that's what this sequence of images is an artist's conception. It's actually out of a movie that's kind of fun, but these are frames from the movie of here's two neutron stars, they orbit each other, eventually they come close enough together that they crash and they merge, there's a tremendous explosion, boom, there's your short duration gamma ray burst. Actually, well, there's a tremendous explosion first of gravitational waves, right? Then it's hot and stuff happens and boom, you get a short duration gamma ray burst here, which again, you have to be looking in the right direction to really see all of it. If you're looking here, you'd still see some, but it wouldn't be as bright as if you were looking here and you saw the jet right along the pole come out. And that doesn't last very long, and then behind you just have whatever is left over, which might be a it depends on the masses of the neutron stars. It could be still a neutron star, but it's more likely to be a black hole because the masses are probably too big to have a neutron star left over. So yes, neutron stars run into each other, and that has been, because the timing worked right and because the energetics worked right, that has been the leading model for what causes short duration gamma ray bursts for quite some time. So two kinds of gamma ray bursts: long duration, they're from a particularly powerful supernova; short duration, coming from colliding neutron stars. Now, both of these depend on massive stars. The first one directly, because it's an exploding massive star. The second one indirectly, because it's massive stars that when they go supernova, sort of medium mass, not the really high mass stars, that leave behind these neutron stars. And so if you want neutron stars, you have to have massive stars going boom for a little while to make them. So great. So now we come to the event. It has the very romantic name. Oh yeah, even the smallest neutron star coming near Earth would kill us all. Now, there's actually a whole bunch of different ways it could kill us. Probably the easiest way for it to kill us is that if it went tooling through the inner solar system, so bear God, I'll get to that in a moment. If it went tooling through the inner solar system, it would be the gravity of something whose gravity was equivalent to the sun, or maybe even a little stronger. It wouldn't have to get too close to us to irradiate us or anything. It would just have to get close enough to screw up the orbits of all the planets. And, best case scenario, we go into an elliptical orbit and our climate becomes unstable and we all die. Worst case scenario, we get thrown out of the solar system and we're sad. So yeah, so a neutron star passing close to the sun would it depends on what you mean by close. If it passes 50 astronomical units from the sun, that's also bad, depending on exactly where it is. It won't directly disrupt the orbit of the Earth, but it'll disrupt the orbit of a whole bunch of Kuiper belt objects and Oort cloud objects, and at some time later, which could be hundreds or thousands or even millions of years later, lots of comets will come raining down through the inner solar system, and some of them will probably hit the Earth and kill all the dinosaurs. And for that to happen, we have to make more dinosaurs. But fortunately, genetic engineering is working on that, so it'll all work when it happens. Now, Baragon says, why does not the entire neutron star glow? So I'm actually going to go back to the pulsar page here. And the reason the entire neutron star doesn't glow, I mean, the whole thing does glow with a hot glow, but it's so small that you don't see it much. The reason is that the magnetic field, just like on the Earth, is very much stronger at the North Pole and the South Pole than it is over here on the sides. Magnetic fields are stronger where the field lines come together. That's one of the things when looking at these magnetic field lines, if you want to visualize it. So the magnetic field is really strong right here, and so that's where it's going to collect all the particles. And so where the particles collect and hit, that's where the hotspot happens. Right. So August 17th, all right, by the way, something that alarmed me when I was preparing for this talk, that August 17th was 3 months ago, almost to the day. And if you go to the astronomy, adsabs.harvard.edu, the astronomy abstract service, there's something like 150 papers about this object already. So people have written 150 papers in the last 3 months about this object. Now, a whole bunch of them were some of the early discoveries, like the people who did optical observations, early optical observations, had papers 1 through 10 in an epic series. So yeah, a lot of it, some of them were the early discoveries, but there's also modeling that's happening. It's just amazing the rate at which stuff is being written about this. LIGO and Virgo are gravitational wave detectors. Like I say, I've talked about them before. They became really famous a while back, not too long ago, a couple years ago, when two 30 solar mass black holes collided, sent out, I mean, of course, the two 30 solar mass black holes collided millions of years ago, but they sent out gravitational waves that we detected a couple years back with the LIGO observatory. Now, LIGO has been, when I was a grad student, started in 1990, the LIGO project already existed. They were building the first generation of LIGO that they didn't actually expect to detect anything because it required various updates, but now they have. And so it was a direct detection of gravitational waves. It was extremely exciting. It was also exciting that we saw two big 30 solar mass black holes colliding with each other, because that's pretty cool. By now they've detected, we're pretty soon going to get to the point where nobody's going to know exactly the number because they'll just keep coming up with them. So they've detected 5 or something pairs of black holes colliding with each other. But in August 17th, they detected this gravitational event. Now, what this plot is a plot of frequency, and that's frequency of the gravitational waves. So you've heard frequency before, either with light or sound. It's not sound, it's not light, it's gravity itself. It's the structure of space-time that's waving, but it's a wave equation. And so what the frequency means is how many cycles per second. All waves go through cycles like that. So it really is the same meaning. Gravitational waves, here's the range of frequencies. Over the course of 15 seconds, they started with basically no signal, but it started getting brighter and brighter. So they saw this brighter and brighter gravitational waves coming in, slowly increasing in frequency. And then they went, and at the last minute, they rushed up to really high frequency, and then boom, it all stopped. No gravitational waves after that. And this is a classic LIGO signature. It's basically the same shape as what they've seen for colliding black holes. So as the black holes come into their final few seconds of life, they're orbiting around each other pretty fast. These frequencies tend to be 100 hertz, 200 hertz. So it's the same frequencies as sound waves, but they're not sound waves. I just want to make sure that's clear. They come in, they get brighter, they slowly increase, but then the rate of increase increases, and eventually it asymptotes to really high frequencies and then stops. And that is the moment of collision. So on August 17th, the gravitational wave detectors detected this gravitational wave, and it was a little different from the ones they had before because it was smaller objects colliding. And in fact, if you remember, or if you've seen some of the plots of black holes colliding, they tend to be less than a second. The whole thing that starts with the gravitational waves getting bright enough, bright in gravity waves. I guess I should say strong enough that that they could detect them to the collision. It's usually less than a second, something like that. And here, this one goes on for 15 seconds. So these are not as massive of objects. They're colliding. They're coming together really slowly, but still, boom, they collided. Now, so then Pepys got excited. But what really got Pepys excited is that LIGO saw this, but also the Fermi satellite and Integral. So basically, gamma ray satellites saw this as well. The Fermi satellite has this thing, GRB oh dear, I don't remember what it stands for. It probably stands for gamma ray burst. No, it's not. It's I don't. Whatever. There is a. Oh, sorry. GBM. There it is. GBM. Gamma ray burst monitor is a instrument that monitors the sky for bursts of gamma rays, and when it happens, it sends out automated alerts, and the automated alerts go to all the people who care about gamma ray bursts, because then they can scramble and try and get their telescopes pointed in the right direction to see if they can see other signals, optical signals, infrared signals, things like that, coming from the event that caused the gamma ray burst. Well, and so what's really cool about this is from the timing of the gravitational waves, right here is the time when it merged. So that's when the signal whoop, diverges to really high frequency. I just like making that noise, so I'm going to keep doing it. But then, less than 2 seconds later, boom, we've got a short duration gamma ray burst. So already, just the fact that there is a gravitational wave event and a gamma ray burst within 2 seconds of each other is highly suggestive, because gravitational wave events don't happen every day. Gamma ray bursts do happen every day, but typically around once-ish per day. Yeah, I know, we don't have flying cars yet. You know, the real reason we don't have flying cars is just go out and watch people drive, and you see how terrible most drivers are. Do you really want them to have flying cars? Yeah. So, already it's suggestive. But then, within 10 hours, so, you know, sort of a typical delay between the gamma ray burst going out and the astronomers being able to scramble and get their telescopes going and pointing. Sometimes it can be faster than that, but within 10 hours, there was optical follow-up as well that saw in the spot of the sky where the gamma ray burst happened, saw a dimming glow of optical light. And so if you put all three together, now what these are, this is sort of an interesting plot, so I'll try and tell you what it means. First of all, this big ellipse oval thingy is a map of the entire sky. It's the exact same projection that I showed you before with the gamma ray burst. It's actually, well, it's the same projection. It's not quite the same map. This gray thing here is where the galaxy, the plane of the galaxy is. So this is actually on the night sky, where this would be the equator. So the part of the sky that's right over the equator. This is the Polaris is right there, the North Celestial Pole. And the gravitational wave detector actually was able to say that the gravitational waves came from somewhere in this green slash, although it turns out there were two green slashes. There was one on the opposite side of the sky. It could have been in one or the other. The gamma rays, so they detect where they're coming from, but you can see it's a big blob. They don't actually get very precise pointing on exactly where it came from. So they knew that the gamma rays were somewhere in this blob, but already that's pretty impressive, because you've got gamma rays in this blob, you've got gravitational waves from a consistent location within 2 seconds of each other. And then the optical follow-up says, oh, yes, here it is, down there inside where the gravitational waves were. And so that little star there shows you where the event was, where it happened. And so by the time you've got all three of those, the probability of there randomly being three different uncorrelated events, you know, something that's a optical explosion and a short duration gamma ray burst that's not connected, and a pair of neutron stars colliding and sending gravitational waves that's not connected, the probability of that just randomly happening by coincidence is like 1 part in billions. So we are very sure that all three of these things were looking at exactly the same event. Also because the modeling of it, that works. You know, we understand what all of these things are, and it works. So this is really cool, because we saw the gravitational waves. We knew it was neutron stars colliding because it emitted gravitational waves just right for that. We also saw a short duration gamma ray burst, which we had thought were neutron stars colliding, but now we have really strong confirmation. So that's one of the cool results of this, is that we have really strong confirmation that short duration gamma ray bursts, at least sometimes, are colliding neutron stars. It's possible also that if a neutron star gets eaten by a black hole, it'll do one, so maybe we'll see one of those some days. We can't rule out that there are other mechanisms we haven't thought of, so we can't say with confidence that all short duration gamma ray bursts are colliding neutron stars, but it's plausible that they all are. And at least some of them are, because this one was. So this is great. All three of these things from the same time. So this is why there's 150 papers on this, because no matter what kind of astronomer you are, observational astronomer, you can probably do things to observe this event. And if you're a theoretical astronomer, there's probably things you can do with this event as well. So lots of people are thinking about this event. It's a seminal event because it, like I said, it opens up multi-messenger astronomy. It opens up connections between gamma rays, opticals, and gravitational waves all at once. It gives us actual data on short duration gamma ray bursts that can really check things. Yeah, they've been traveling for let's see if I can do this at the top of my head, like more than 100 million years. Yep. That's actually an excellent point. In fact, I think that's the point on my next slide. So thank you, Astrid. It's almost like I planted you in the audience. The gravitational waves arrived within a second of the light waves. And all the light waves, so here's the thing. We don't know if optical light arrived at the same time as the gamma ray light because it was 10 hours later. But the gamma rays, which are light, photons, and the gravitational waves arrived within less than 2 seconds of each other. Now, there's reasons to model to expect that the gamma rays might be emitted slightly later because it takes some time, a second, for those shocks to develop to send the gamma ray burst out. That's right, yeah. Well, it actually doesn't suggest, I say it more confirms the source of the gamma ray burst. Yeah, because already that was the leading model for what it was. The fact that they came, but even if you make the assumption, the conservative assumption that the two events, that the gravity and the light were emitted at exactly the same time, it still says that the speed of light and the speed of gravity have to be the same to 1 part in 10 to the 15th. So, speed of gravity moves at the speed of light. That is exactly what general relativity tells us. General relativity tells us that gravitational waves propagate at the speed of light. If you want to talk gravitons, the graviton would be a massless particle. We haven't actually discovered the graviton, so, it's even conceivable that there is no such thing, although I think most physicists would consider that heresy to think about out loud. But the graviton would be a spin 2 particle. It would be massless, and in relativity, everything that is massless moves at the speed of light relative to everything else. Photon is the particle of light. We have detected scads of them. In fact, it was strong evidence for the existence of the photon that got Einstein his Nobel Prize. Baragon, I thought you said you were a gravity skeptic. Because if you're a gravity skeptic, never go outside, because you're just afraid you're going to fly off into the sky. So photons and gravitons both would move at the speed of light, according to relativity. And yes, you could think of the gravitational wave as a big, gigantic collection of gravitons, just like you can think of light as a big, gigantic collection of photons. The difference being we understand photons really well and do all kinds of experiments on them all the time, and we've never detected a graviton as a graviton. We've just had gravity. So, yes. Yes, exactly, Joe. Thank you very much. The weight of evidence proves gravity exists. She will be here all week. Or he. I don't know. Joe, you could be either. So, yes, under conservative assumptions, gravity and light move at exactly the same speed, which is pretty cool. I mean, again, this is an extremely strong constraint. There had been constraints before. I don't remember exactly how they did it or what it was, but there was something having to do with measuring the effect of Jupiter, where they had constrained gravity and light to be moving at the same speed before. But this is an extremely precise constraint, partly because, as I think it was Baragon pointed out, or somebody pointed out, they'd been traveling for hundreds of millions of years, and they arrived within seconds of each other. So there you go. I mean, if you can be precise within seconds over hundreds of millions of years, then the conductor can't complain that you're not counting very well if you're in an orchestra, which these weren't, because they were neutron stars, and neutron stars don't play. I have no idea what I'm saying. So let me get back to my talk. So that is one cool result of that is this. Now, I do want to talk about the optical afterglow a little bit. It turns out it was in a galaxy that has a name. Well, it has a number, but it has a sort of, it's a nearby galaxy, as these things go. You can see the galaxy here. This is actually a Hubble Space Telescope image. So August 22nd, within a few days, they got the Hubble Space Telescope pointed at it, which is about the best you can do. Back in the day, in the late 90s, early 2000s, when I was with the Supernova Cosmology project, we would follow up supernova with the Hubble Space Telescope, and we'd discover them, we'd confirm them. It usually took us a day to confirm them, and we'd get the information to the Hubble Space Telescope as soon as we could, and at best, it was a couple of days before they could get the Hubble Space Telescope actually taking the data on it. So this is, the fact that it was a 5-day delay means, yeah, the Hubble Space Telescope jumped on this. And here they are. They see this spot here. Zooming in on the spot, here's April 22nd, here's April 26th, here's April 28th. The spot is fading away as gamma ray burst afterglows do. So remember, the gamma rays faded in less than a second. The optical afterglow fades over the course of days or weeks. And that's what we're seeing here. So yes, we're seeing this. This is the thing that told us exactly where this little guy came from. And the galaxy it came from was NGC 4993. So if you know anything about astronomy, you know if it has an NGC name, that means that it's been cataloged for a long time, and it's a relatively nearby galaxy. Distant galaxies don't get names that start with NGC. New General Catalog. Basically, it's a revisions of catalogs originally created by William Herschel hundreds of years ago. So NGC, and I said it was close. It really is close. 40 megaparsecs, that's like 130 million light years away. Now that might sound like a long way to you, but if you're a cosmologist, 130 million light years is what you call your backyard. It's very much the local universe. The look back time, 130 million years, is nothing compared to the 14 billion year age of the universe. This thing is closer than the Virgo cluster. The Virgo cluster is something like 65 million light years away. So the Virgo cluster is what, it's the closest big cluster of galaxies. It's kind of like it's the big kid on the block, but it's still on the block. So this is a really nearby galaxy as these things go. This is a paper. So one of the papers was, hey, let's measure the distance to the galaxy as well as we can. And there you go. There it is. The type of the galaxy is an SO galaxy, sometimes called a lenticular galaxy because it's kind of lens looking. Galaxies, big galaxies, broadly speaking, can be divided into spiral and elliptical galaxies, and a lenticular galaxy is right on the border. So a spiral galaxy is dominated by a disk. You usually have some kind of spiral arms, or at least spiral armlets you can see in it, whereas an elliptical galaxy is a big blob. It might be a big sphere, but it might be like a football shape, but it's a big blob of stars. And then this is something that's got a disk, but the disk is pretty wide, and it's blobby plus disky, and there's not all that much in the way of spiral arms, although you see some structure here. But I suspect the structure we're seeing is not spiral arms as much as leftover ringing from a previous collision, although there's some tomato with that. Anyway, so it's a pretty normal galaxy as galaxies go. So yeah, 4993, it depends on what book you have. It's not the brightest galaxy in the world, so it's not necessarily, if you have a book for a small telescope, it won't necessarily list it, but it is in the NGC catalog. So one of my favorite places to go and look up information on galaxies is this. I will type it in here. NED, or the NASA Extragalactic Database, is something that's been around. My advisor in grad school was one of the people who was in charge of the institution that created this when I was in grad school. So I used NED even before it had a web interface, when you had to send an email with well-formatted commands and it would email you back the information you had asked for. So NED, so you can go look up NGC 4993 there and see what they say. I haven't actually looked it up there, but see what they say about it. So yes, that's the galaxy it happened in. Pretty close galaxy, lenticular galaxy. The fact that it's a lenticular galaxy tells me that it probably hasn't had very much star formation recently. These neutron, but, well, in the past it did, because it has stars. So these neutron stars have probably been hanging around for quite some time, orbiting each other for a long time, billions of years probably. And only now did they finish their in-spiral and collide and make a nice little boom for us to look at. Now this is sort of a nice little picture of models of what happens when these two neutron stars collide. It's not a simple, crash and then they merge. All kinds of junk happens, and it depends on, there's lines here drawing winds that happen, and it depends on the details of what happened, whether you get a very strong very narrow magnetically confined beam in the middle, or whether you get a broader central beam. And then how much you see depends on the angle you're looking at. So if you look straight down this beam, you'll see it. If you don't, you won't. Here, you might see sort of the edge of this. It won't be as bright, and you'll see a lot of this. If you're looking at it from over here, you wouldn't see any of that. You get that. You also get an explosion that goes around the equator, and it's probably more probably closer to spherical, and you get a bunch of ejecta, a bunch of junk is thrown out. And that is where the gold is. So in addition to the two neutron stars colliding and leaving, colliding and whatever gets behind, a lot of the junk is thrown out. And the junk is thrown out in the middle of a gigantic explosion. So much like a supernova, when the junk is thrown out, there's huge amounts of energy present. And that huge amounts of energy allows elements to fuse even when it's not energetically favorable to do so. So remember, you could only get up to iron at the core of a star because it costs energy to fuse to higher things. But during a big explosion like this, you have energy all over the place, so some of that fusion is just going to happen. And yeah, where the gold is. We'll get to there in a moment. So this is a paper from, this exact plot is from this Pion paper. Both Pion and this Kaysen paper, and incidentally, name drop time, Dan Kaysen was a grad student with the Supernova Cosmology project when I was a postdoc there. So I recognize that name. He was a theorist working on radiative transfer calculations. Yeah, there's lots of neutrons around, and that really helps with some nucleosynthesis things. But both of them cite a range of 0.03 to 0.05 solar masses of material ejected. Right? And for comparison, Jupiter, if I remember correctly, is something less than 1/1000th the mass of the sun. So the amount of junk that got thrown out is, at least tens, maybe hundreds of Jupiters worth of stuff. And that got thrown out. Now these plots here actually, so what they do is they look at the optical spectra. So we don't just take pictures, we also put a prism in and look at the spectrum. So what does it look like as a function of wavelength? And if you know your wavelengths, actually optical is down here. This is sort of reddish light, and then we get up to infrared light. So the optical and near infrared spectra, the black is the data, the red is their model. They're doing okay here. They're not doing as okay out here, which is why I leave this quote here. This is from the Pion paper. It says, yes, it's not completely out. It's because I was looking at this thinking, wait, guys, do you really think you have a really good model? I'm like, well, we have an okay model. It's like, yeah, okay. But they don't have a perfect model. So they know it's not perfect. So if you've read precise numbers about how much of any given thing was produced, we don't really know it that well. This range is probably about right, but exactly how much of which element, I don't think we know all that well. But we do know, we can model it enough that we do know a lot of stuff was thrown out. And a lot of and these models are based on a model where a lot of really heavy elements get created through what is called the R process, which is a nuclear fusion thing, or nuclear neutron nuclear thing, where if you have whole bunches of extra neutrons, which you would in this case, you can do lots of that. And in fact, putting this together with lots of other things, you can come up with a very interesting view of the periodic table. So you've all seen the periodic table before, I hope. If not, I don't know, go take chemistry. The colors here tell you where did the elements come from. Now, I've given talks before where I've talked about where the elements have come from, but usually I'm talking about the Big Bang. And you can look at this and see the Big Bang gave us hydrogen, and it gave us helium, and it gave us a really tiny trace amount of lithium. You might look at this and say, no, that looks like a lot of lithium. Well, you have to remember that the total amount of lithium in the universe compared to hydrogen is well less than 1%. So, Big Bang gave us just these two things, pretty much. Wee bit of this, and that's it. That's all we got. Everything else was made in stars. Exactly how in stars? Well, lots of ways. This is one that actually kind of fascinates me because there was a time when I didn't realize that low mass stars actually did some nucleosynthesis, especially these heavy things. Exploding massive stars. So that is the type 2 supernova. That's the supernova at the end of its life when it's got iron at its core and it explodes. Interestingly, it does not send much iron out because most of the iron was at its core, but basically all the moderate mass elements. So your oxygen, right? Take a deep breath. You are breathing supernova. The oxygen, but you mean you're also breathing dying low mass star because the nitrogen, but the fluorine, the neon, the sodium, right? Go salt your meat and you're eating supernova. The magnesium, the aluminum, right? Go drink a soda. You are drinking from supernova. All right, so all those great things happen. Then exploding white dwarfs is the other type of supernova. So that's when you have either two white dwarfs run into each other and explode, or a white dwarf is pulling matter off a companion, gets too big, and explodes. That's a type 1 supernova, or a thermonuclear supernova. Lots of fusion happens in that as well. I will give you a link to this graphic shortly. That's what these gray ones are, and that's where most of the iron comes from. That's where we get our nickel. That's where we get our zinc, our copper, right? Our vanadium. So colliding white dwarfs gives us lots of stuff. But here's the really neat thing. Lots of elements, like, for example, gold, most of it probably is made in these merging neutron star events. So these merging neutron star events made all this purple stuff, including gold. I don't know why we're so obsessed with the gold, but maybe just because we think of gold as being really valuable, I guess. But, you know, we could also talk about the radon and see, you know, you think about all the poor little people in space getting lung cancer because they have radon gas now. Things like that. All the way up, except, of course, here, there's a little problem that these elements aren't even stable. So and probably they were made in the colliding neutron star, and then they fell right apart. So we make these things ourselves in our colliders, and there's actually more than 103. We've gone up to 108 or 113, I don't even know. And uranium, right, you need that if you want to make fission bombs, which is very important for civilization because that's how we end it. So, yeah, lots of stuff made in neutron stars, and it's really cool. So where did I actually, this graphic, let me give you the link to this version of it. So the link at the bottom is actually a professor at Ohio State who put together an original version of the graphic. And I need to, actually, back in January or something, I looked, she put it on a blog post, and I haven't seen the follow-up on how she actually figured out the numbers she used for all the fractions. But this version was based on her data. So let's see if I can find it. I am searching. Maybe it's this. Oh, it's not that. It's almost that. Okay, you know what? I'll do it at the end because I don't want to slow myself down too much. I didn't find it immediately. All right, one other bit of science that came out of this. It turns out that we understand, well, I don't understand, general relativity allows us to model the collision of neutron stars well enough. And we know the distance to this galaxy. Well, actually, all right, we're going to find another way of calculating the distance to this galaxy. We're modeling it well enough that based on how strong the gravitational waves were, we can figure out how far away the galaxy is. And what's cool about that is that it's a completely different way from finding the distance to the galaxy to all the other ways we've used before. And one of the reasons we want to measure distances to galaxies is to measure the expansion rate of the universe, which is the Hubble constant. Now, when I was starting grad school, the Hubble constant was uncertain to a factor of 2. In fact, a lot of people thought it was kind of a joke in astronomy that we didn't know the basic cosmological parameter, the expansion rate of the universe, whether it was 50 or 100 on the units that we use. Well, in the last 20 years, we've done a lot better. We got it down to a few percent. Although we kind of have an embarrassing thing in cosmology right now. So here are the units of it. And now we've sort of got two different favored values. One is based off of looking at supernova and all kinds of things put together. That gives us like 72, 73. But then there's the value where you just use what came out of the radio Planck satellite, and that comes more like 68, 69. Now this discrepancy is nothing compared to the discrepancy when I was in grad school, but you notice these lines don't overlap. And so this is an outstanding problem in cosmology right now, the tension between different measurements of the Hubble constant and what's going on there. It either points us to a systematic in one or both of these measurements, or it points us to something going on in our universe that we haven't accounted for properly. This blue line here is the probabilities for what the Hubble constant is given our colliding neutron stars and how bright they were in gamma rays. And what this says is, I mean, you could view this as a way of measuring the Hubble constant, and hey, it's, you know, the peak of it is nice where everything else is. But it's also, to me, it's more, I mean, I trust both of these Hubble constant measurements, even though they're not entirely consistent, better than this measurement. To me, what this really says is more strong confirmation that our general relativistic models are good, and we are modeling all the stuff properly, and we know what we're doing. Right, so, summary. This event was the most distant multi-mode astronomical observation that's been made, because supernova 1987A was in a satellite to our own galaxy. It's the first connection of gravitational waves to light, the first direct connection of that, where we observe the same event, both in gravitational waves and light. One cool thing, the speed of gravity is the speed of light. If you have some wacky model and some of the alternative models to dark matter, it predicted this to be quite different. And so some of those models are now ruled out, not all of them, but some of them are ruled out because of that. But the speed of gravity is the speed of light. In fact, I prefer calling it the speed of space-time, because it's just the natural speed scale of our galaxy. It's not a property of light. It's a property of anything that's massless. We have direct confirmation that short gamma ray bursts are, or at least some of them are, colliding neutron stars, right? We thought that was a good model. Look, we saw something that was definitely a colliding neutron stars, and it was a short gamma ray burst. Lots of heavy elements are made in events like these. We will see more. These things will happen. If we keep watching, eventually LIGO is going to see more of them, and we will be able to get more observational constraints on what these things are doing and understand them better. And then finally, it seems that a lot of the exciting astronomy news in the last couple of years has been dominated by LIGO. So, hey, LIGO, we're really happy you actually finally started detecting things. So I will stop there and take any questions that haven't been asked already. A link to the periodic table. Here it is. Yeah, thank you. Some more details here. And what's good about this is that, oh wait, this is an older version. I didn't find it. I thought I found it. I didn't. Moments. It's coming. It's coming. All right. Well, okay, so gravitational waves. All right, so there's a few reasons why you can't find information on gravitational waves. We've been aware, actually, Einstein predicted it way back in the million years ago. So gravitational waves is a thing that's been known about for a very long time. We confirmed their existence in the 70s, but we've also known that they're an extremely difficult to detect phenomenon. So LIGO is, they have an evacuated tube 30 kilometers long that they shoot lasers through in order to detect it. So they're very hard to see. And so I think, and here's the other thing, if you really want to understand what they're doing, the math is a little, is beyond what most undergraduates will do. Like I have a very good, sort of one of the best undergraduates at Westminster is going to be doing an independent study with me on general relativity next semester. He'll probably actually do some of these calculations, but most physics undergrads don't even calculate this. So a lot of books won't get into them because it's hard, and because only recently did we directly detect them. But lots of books will mention them too. But until recently, they've been pretty esoteric topic. Another thing, Baragon actually asked, I think it was Baragon, could you see the effects of gravitational waves on time? Directly observing that, I think, would be incredibly difficult. We have used space, so the distance between things, to detect them. We have seen relativistic effects on time a lot, with the time dilation from both general relativity and from things moving fast, special relativity. But seeing the time dilation effects of gravitational waves, I haven't actually done the calculations, but my instinct tells me that they would be many orders of magnitude more difficult than what LIGO is doing right now. So it would be tough. Right, is gravitational waves a disturbance in the quantum field? Okay. Okay, so first of all, gravitational waves, as we theoretically describe them, is actually a disturbance in space-time. It's a non-quantum model, general relativity. And so it's a wave-like disturbance, much like sound waves are a disturbance in the density of air. However, most of us suspect that, yes, there will be a quantum theory of gravity because we believe, I don't know if I believe this anymore, I'm kind of an iconoclast, but probably, no, if I'm honest, I probably believe it, that everything is ultimately quantum. And so there is a quantum theory of gravity. And so then that means there's going to be something like a graviton quantum field. Now, it turns out that just gravitons itself are a disturbance in a quantum field. That's what particles are, disturbances in quantum fields. So then, yes, gravitational waves would be a disturbance in the graviton field in that case. But we don't even have a working theory of quantum gravity, never mind a detection. It's not a topological effect, it's a geometric effect. So it has to do with just the local distances between things as opposed to the connectedness of stuff. Still trying to find that periodic table, and I don't know why I'm having so much trouble because I found it very fast the other day. Here it is. Yes, I found it. Good. All right, and here's the good thing about this. For those of you who know it, yeah, it's exactly what it's like, the watch pot. Although it says PNG there, that link, if you go to it, there's an SVG file there as well, which is, I thought it was an SVG file. Why is this not an SVG file? Oh my goodness, I still didn't find the right one. I'm like the worst person I know. The watch pot not only doesn't boil, it doesn't even exist. The Russian translation. Yes, this is the colorblind friendly one, which is fine. But what I'm looking for is the one that I actually showed because I think it looks a little better. You know what? I haven't found it. We will pass it on afterwards. Sorry about that. Are there any other questions? Any chance of observing super heavy elements that might be long-lived enough to give absorption lines and spectra? I'm assuming by super heavy you mean like element 108 and things like that. I would say probably not, because their lifetimes are tiny, fractions of a second, and by the time we could get our telescopes pointed and start taking a spectrum, they'd be gone. They'd be made and gone way too fast. So my guess would be that that's prohibitive. Oh, cool. Yeah. So Westminster College is where I live now. Let's see, or where I work now. Models are the models completely. I don't know exactly the details. I'd say that there are revisions to be made, and if for no other reason, just because of the imperfections of the match here. Those are probably more detailed revisions than revisions in terms of the concept of it. So yeah, there's going to be revisions like that to be made. I think the general relativistic models are still quite solid. But these revisions are probably more of what exactly are the parameters that go in, or what exactly was the stuff that was there, as opposed to do things work the way we think they do. Okay, so if something has a 333-day half-life, then potentially we could see that if there was enough of it to put in an absorption line, right? Because there it definitely would be in the ejecta. Now, part of the problem also is that these ejecta are moving at very high speeds. So there are features you can see like absorption lines and stuff here, but they're very broad because things are moving fast and things are moving at lots of different speeds. And so lots of lines are all going to get mixed together into one. And so it's going to be really tough to separate out lots of stuff. It's one of the other things that makes this hard. Oh, that's an interesting idea. Yeah, island of. Um, maybe, but my guess is we don't know. We don't have good calculations of exactly where those lines should be, that we might not even recognize them. And the same thing I just mentioned of these big, broad lines, they'll all get buried in that with other stuff. That's a neat idea, though, of thinking, this is where they might be created, and maybe could we see them somehow? I don't know. I'll go find a spectroscopist and work on that and write a paper. See if it can be done. It has to do with bagels, I think. Let's see. All right, here it is. I found it. And it is an SVG file, like I promised. So if you know what that means, you will be happy, because it's a vector file as opposed to just a image file. So, and that was the one that I showed. All right, well, thank you all for coming. I'm going to head out now, and if I'm going to be honest, I'm probably going to take a nap. So thank you all for coming, and I will see you all in the future. Well, see ya.